Okay, so here we go. Warm welcome and very good evening. So, yeah, Asif, you have a question before we begin? Okay, so physics for students, I welcome you to Einstein's General Theory of Relativity. So, first, what I would do is that I would like to give you a few interesting facts that it was published in 1915, Einstein's General Theory of Relativity. Okay, let me make the screen a little bit bigger so that it is visible much clearer. I think this is best. So, and what it shows is basically that it describes gravity as the curvature of space-time, which is being caused by matter and energy. And it tells that there are objects, massive objects which are going around around the fabric of space-time, which causes in the curves. I mean to say, this is a very gross and a very basic understanding. We will go more into that. Now, here you see there are certain very interesting facts. Fact is that on the 4th of November, on the first draft was published on the General Theory of Relativity. Then again Thursday. Then on next Thursday again on General Theory of Relativity. Again on next Thursday 18th again an explanation of the perihelion precession of the Mercury, which is the prediction, and then on 25th the final paper, so field equation of gravitation. Could you use the full screen? Okay, let me see. You should tell me now whether you can see it on full screen. Is it visible, the full screen part? Yes or no? Can you just unmute
No,
and
sir.
tell me?
Not.
How will I do the full screen? I don't know. I mean to say, wait. How will?
So
Yeah,
I think
I think.
you can click the slideshow thing.
I just did that. This is now full screen on my screen. I can see it is full screen. Can you see the full screen part? No.
Yes, sir.
Sir,
Is it?
everyone's have option there.
What?
So there
On
is
the
an
right hand,
option.
lower right hand.
No, no, but again and again, you see there are a lot of people who are joining. So again, I have to lower it down and I have to admit that. So let us go ahead with this, right? A lot of people are constantly joining. So if I make it full screen, I won't be able to see my Google Meet screen. I'm trying to make it a little bit more bigger.
Yes, is good.
Is it good? But it is going out of screen. Let me see if I can. Yeah, this is
It's good
better.
now.
It's good now. Okay. So this is a kind of a historical fact that everything happened on a Thursday. Now I don't know how important Thursday is for you. Okay, these are few of the important revolutionary facts that it actually, revolutionized our understanding because it predicts phenomena like gravitational lensing, etc., and it has got cosmological applications. Okay, so that is this is a very gross understanding. Now, here I would like to tell, especially for the people, young people who are joining in. Now, there are a lot of challenges in relativity. You know, what are the challenges? That where to start, what to read, how much time do I dedicate? Can I really learn it, or what are the degrees of complexity that happen? So these are the things that keeps on wondering in your mind, and Devopratim has got a nice background of a spaceship that looks really nice. So these are the things, and finally it comes to a question that can I at all do it, because there is so amount of exotic mathematics which are involved. Now you see, whenever you talk of general relativity, the first thing, now this is very important that you need to understand, the first thing comes to your mind if you go to internet and search is this kind of a thing. You all agree to this, isn't it? That there is a mass, there is a space-time thing, and there is something heavy and which is causing a dent, right? It creates a dent, it creates a kind of a dip, and the dent is on a grid, something like everywhere you type out general relativity, you will see this. Now, if you talk to pure mathematicians or people like that, some of them might say, I think Dr. Azizur Rahman, my kind regards, he has joined, he is a faculty of mathematics from Northeast. So welcome, Dr. Azizur. So some of the people will say, no, this is not right, this is not mathematically right, etc. But I would say all of them are right. All of them are right. I will tell you the reason. Now you see, before moving into general relativity, what is important, when you see classical physics, you see a pendulum. Okay, it is going forth and back and forth and back, right? When you see quantum physics, you people are joining quite late. So you see that there is a nucleus and there are, things which are going around, right? But in general relativity, you see something different. Now, try to understand what I'm trying to tell. What different that you see is that it is neither related to a pendulum, nor a nucleus, nor atomic or physical things which are going around, but a kind of a geometric structure. Are you getting me? You let me know if you are not unable to understand. This is intuitive. So I mean to say, there is a geometric structure which is being done. So first question is that what causes this curvature and what this picture actually means. And that is why I always tell my students that before you do anything in general theory of relativity, the first thing is that you need to understand geometry. I will tell you why. There's a very deep underlying reason. And non-Euclidean geometry, and what is the book that you should read in non-Euclidean geometry? I won't tell the book name right now because I have made many videos on the step-by-step approach to general relativity. I will give those links also when I issue the certificate, because as I told you that it won't be possible for me to cover such a huge, enormous ocean of sea in 1 or 1.5 hours. Not possible. So remember one thing, that the basic difference in terms of visualization is what? That there is a dent and there is a heavy mass which is causing that dent. Now, before I move into that, I need to tell you what is a system. Now, this is again very important. By system, I don't mean a thermodynamical system or something, but something very deep and which I have learned from my professors, etc. And this is somewhere we really do not pay attention. And we directly jump into the mathematics of general relativity, black hole, white hole, time travel, all those superficial talks. Before going to that, I would like to go ahead and define you what is a system. This is the first basic building block of general relativity. Okay, so just to ask you, is it all okay till now? Everybody can understand everything? Everything
Yes,
is
sir.
fine.
Yes,
See,
sir.
this
Yes,
is
sir.
my habit.
All right.
Don't take
Yes,
me
sir.
wrong, because I have a habit in my class also, time and again, summarizing and asking whether you can learn, because there are so many people, I cannot see everybody except Muhammad, and the Pratim is riding on a spaceship. That's really nice. Okay, so when I talk of a system, now pay a little bit of attention. This is something very deep. This is really really deep. There are primarily three type of system: a classical system, which is very deterministic. I will come to the reason of this, telling why. The second is a relativistic system, and third is a probabilistic system. Okay, uh, Mohammed, can you just mute yourself? There's a sound coming up. Yeah. Okay, so this is a probabilistic system. Now, here what happens is that when you talk about modern physics, there is nothing called modern physics. There is either a classical physics or a relativistic physics or a quantum physics. Modern physics is an era. It is a time that after 1930 or so, we call it as modern physics. So if you talk of physics, primarily these are the three things: system, classical, deterministic, relativistic is also deterministic, and quantum is probabilistic. Okay. So now you see here that classical system, when we talk about it, we call it Newtonian mechanics. Okay. Quantum system, I will come to the relativistic. This is determined by your wave function. Wave function means you know that the particular state of a system is determined by a wave function. But it is because we cannot tell that the electron or the proton or positron will be there. There's a probability. Now, third thing that comes up is that special and general relativity is a relativistic system, but it is more of a geometry of space-time. What do I mean by that? Let me explain you now. Now, this is a basic question. I remember I talked to a Russian physicist. What was her name? I don't remember. He actually introspected and told that, Shaunak, you are going wrong somewhere. You talk about relativity, general theory of relativity, and GTR. And this is my understanding that general theory of relativity, this is again very important. Please do pay attention. I'm trying to go deep into the philosophy. is not much about what we call as relativity. I mean to say a relativistic thing. It is not. Let me tell you what do I mean by that. Okay, so sorry, so what I call is that this is my term, it should be called more as general theory of geometry. Now why I'm telling you, let me explain you that. Now pay attention to this screen. Now those who have done my volume, okay, okay, just a second, I think this is much better. So, those who have done special theory of relativity, you know that special theory of relativity deals with all those left hand side things, right? I think Achal and Prasant and Giles, I mean to say, you are all aware about it, right? Inertial frame deals with speed and velocity, experimentally provable, etc. So, what I am trying to give you an idea is that special theory of relativity is what? It is a study of relativity and simultaneity. That means speed talks about the speed, time, and space. Do you all agree to me or not? Special relativity, what we speak about, speed of light is constant, then there is a time dilation, there is a speed factor, then there is a length contraction. You agree to that,
Yes,
all
sir.
of you? Okay.
Yes, sir.
Yes,
Yeah.
sir.
You see on the right hand side what I am talking, it is general relativity. It speaks about non-inertial frames, gravity, geometry of space time, and a large scale. That means it is a study of geometry. Now you might say, sir, why are you telling me that? Because I want to make you mentally aware and mathematically also aware that you are not learning the usual mathematics in general relativity. See, until you make yourself aware that these are the things which are going to come, how will you make yourself aware? Otherwise, you will always say, sir, general relativity is difficult, difficult, difficult. No, it is not difficult. Are you getting my point? I will show you further things. You see this screen. All these things are components and mathematical notions of general relativity. Space time, tensors, Ricci curvature, Christoffel symbols, metric tensor, affine connection, parallel transport, etc. In today's webinar, we will cover up a lot of stuffs like this. But you see, these are all related to geometry. You tell me where length contraction and time dilation and Lorentz transformation. Do you see anywhere, Achal and Anuj and others? I cannot see the 38 people are there. Can you tell me that where do you actually see the usual mathematics of special relativity? You don't, isn't it? Tensors are what? Something related to geometry. Curvature scalar same, parallel transport same, black holes also same, geodesics also same. Do you agree with me or not? I mean to say, you don't have to tell, but because I am telling and you're attending, do you agree? I mean to say, can you get a idea what I'm trying to tell?
Yes, sir.
Yes, sir. Sir,
We
Okay.
are not, assume we are not 3D world. That's why we are not,
Huh? What?
so
Achal?
what about topology?
we are
Topology
not
is
feel this in three-dimensional world. That's why.
absolutely. Absolutely. See, topology is a subject of pure mathematics. Yes, you're right telling that topology also deals with a geometry of space time. It is a very good question, but it speaks on a global scale. I will come to your point, Anuj, that why we are not dealing topology in general relativity. That's a very intelligent guess. I will answer to this question in a few minutes' time. So you see here, I will quickly glance over all those things, black hole, frame dragging, etc. They are non-linear in nature. That means it doesn't go in a linear structure, it goes like this. And they are very covariant in nature. What is covariant? I will come to that later. That we will deal when we were dealing with tensors. Okay. And here you see, this is the important thing, all the relativistic things. Now this is important because generally teachers, I'm not criticizing, sorry for that, but generally teachers do not deal with the motivation part of general relativity, directly go to tensor calculus and differential geometry. No. So all the special relativity effect, when you generalize from 1905, Einstein formed his special theory of relativity. And remember, it took 10 years, 10 long years for a person like Einstein to develop general relativity. Why? Because there is a paradigm shift. Why? It was a new theory of geometry. Why? Because there's a complete change in mathematics. Why? Because our understanding totally changed. You got my point. So this is the why and now you can ask me that, Shaunak sir, can we learn general relativity without special relativity? Now my answer is going to make you surprised. Yes, you can. Yes, you can. And I also did that. I jumped into general relativity without much knowing special relativity because the mathematics is totally different. Riemannian geometry, Riemann curvature tensor, I will come one by one, one by one. Let me first set the stage because otherwise other people will be confused. I will come to that. So now you see all those things: length, contraction, time dilation, mass, energy, speed of light, all of them are now being transitioned. I think it's a wrong English. There's a transition to tensors, geodesics, parallel transport, Riemann curvature tensor, and all those things. So, what I'm trying to make a point is that general relativity is more of a geometry rather than relativity. So, remember, somebody asked me this question, that why general relativity is difficult, why special relativity is easy. So, the answer to your question is not that of the mathematics. No, you know mathematics much better than me. Right, but the problem is that geometry means visualization, geometry means intuition, geometry means abstractness. So if I say that imagine a straight line, you imagine it. Let there be a perpendicular, let there be an angle which is coming in, so you have to close your eyes and imagine. But in special theory of relativity, you directly can do the sums, do the mathematics. There is also the thought experiment, but this is very much intuitive in nature, very much intuitive in nature. And as you understand, don't take me wrong, everybody's intuition is not that good. I mean to say, everybody's intuition is not that hard. So the thing that you need to understand is general relativity. When you are learning, when you are opening the book of general relativity, first get hold of a good understanding of non-Euclidean geometry, hyperbolic geometry. And that is why I recommend the first book is From Euclidean to Non-Euclidean Geometry by Steven Greenberg, which I will give you the link, you can watch it. Sir, do we also deal with D brains in general relativity? No, 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 absolutely not. D brains are something which are related to string theory, which is a kind of a, I would say, understanding, an attempt to unite quantum mechanics and general relativity. But the topic that we are talking is about classical relativity, where D brains and this brain structure are not dealt with. This is dealt with string theory, which is an attempt to unite string, general relativity and quantum mechanics. So all of you till now, you got a point that why general relativity is more geometric in nature, and why we need to understand more of geometry rather than the usual mathematics which is dealt in special relativity. All of you clear? I mean to say, can you all say yes?
Yes, sir.
Yes,
Yes.
sir.
Okay,
Yes,
great.
sir.
Sure. Yes. Yes.
Okay, fine. Okay, now I will come to this part, that what is a classical system, not the usual classical system that you think of a Newtonian mechanics or pendulum, etc. Let me go a little bit deep now. Why I will tell you that, then you will understand. So, in general, classical system speaks of this. There is a deterministic and a reversible. Now, let me explain you what do I mean by that. So, if there is a pendulum and we know the initial conditions, the mass, velocity, etc. So it goes on here and here and here and here, right? So I can tell that if it starts moving from here, well, where it will go, where it will land into, and from there, where it will again come back. So deterministic means given the initial conditions, I can predict that if I throw the ball right on the wall, which I can see in my room, it is going to come back. And it is approximately, if I take the law of average, it is going to land over in this place. That means it is reversible. Reversible in the sense that mathematically I can revert it and I can find that where it will come, and again next few seconds where it will go, just as the pendulum. Now, this is something which is called a closed system. I'm just glancing this because maybe some of you know that it does not exchange any interaction. And if the system has got a kind of a head, just a head, so we take a coin. Imagine that coin has got only a head, okay? And if I say that from head, if I flip it upwards, where it will go, it will again land up to head. So from head, if I go, I will get only head, 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 etc. So that means the state space, if I talk of a coin, it is only head. If I take this kind of a coin, which has got a head as well as a tail, and if I start with the coin which has only got a head, I will go back to head. I mean to say, if the dynamical system evolves with time. Now remember there, this is something which I told, evolves with time. Just remember this word, because this is going to come in a few seconds. Evolve with time is called a dynamical system. And with a tail, it will also evolve with time and will go to tail, tail, tail. But if it is a head, then it will go from head to tail to h to t to h to t. So head, tail, head, tail, head, tail, head, tail, in this way. So this is typically what is called a classical system. Now pay attention over here. I cannot show the animation right now. My videos have got this. Now suppose from 1 I go to 2, 2 I go to 3, 3 I come back to 2. Now suddenly I am saying that you stand at position number 2. Suddenly there is a man who is at position number 2. Now, if I ask that from 2, where will you go? You will say, I will go to 3. But if I ask you that where you were, again, where you were before point number 2, you don't have any answer. Are you getting my point, all of you? Or is it a little bit confusing? Shall I repeat it?
Yes, sir.
Yes, sir,
You
please
got my point.
repeat.
What I am telling is that suddenly, if there is a person who is standing at point number 2, that person has got no past. Okay. Yeah, I am repeating, Saurav. That has got no past. That means the person does not know where he has come from. But the person can tell where I will go from 2 to point number 3. This is what is called the irreversible system. Now, you might say that why, sir, are you telling what is reversible, irreversible system? There is a reason for that. So, irreversible system means a system which spontaneously comes up suddenly. And if it comes suddenly, then I can look, oh, where I was earlier, I don't know. I really don't know. Right? If I say that suddenly I am sitting here, will I know my childhood, my school days, my parents, etc.? No, because I don't have the past. And this is what is called an irreversible system. Let me explain you again a little bit more. Now here I will say that this irreversibility actually happens in a quantum system. This you already know, so I will quickly run past. The quantum system is determined by what? That is called a so it is the same chemistry reaction times. Yeah, it is. Yeah, you can say, Swati, more or less a chemistry reaction type. But we are talking of the physical interaction. So yeah, I mean to say, I can guess why you are asking. So you are on your way. You are right, Swati. So it is denoted by this wave function psi, and you can say that the electron can be here, can be here. You really cannot say exactly the electron is here, or it will, through evolution of time, that the electron will be there. You cannot say. Only you can say that there is a high or low probability that in this zone the electron can be. Now, can you guess why I am telling you this? Previous to this, I just told you in this slide that an electron or any quantum system here, you can probably guess where it is going, if it is H or T or H or T or H or T. You can tell where the system will land because this is a classical system and it evolves with time. But here you cannot tell. And this exactly happens with what is called is a spontaneous emission, which I think who was talking, Swati was talking. And this is exactly, as I told you, Swati, this is the reason. No, so I come to this point. So spontaneous emission is like the fireflies or the neon lights, spontaneously it emits. That means it transits from an excited energy state to a lower energy state. Now you might be guessing, am I teaching you quantum mechanics? No, no, no. I'm teaching you, or we are talking about general relativity. Now you see here what happens that uh, a spontaneous emission is something which spontaneously evolves a quantized amount of energy. That means classical electromagnetism, classically, is not quantized. Obviously, it is not quantized. So, because it is not quantized, in the absence of quantized electromagnetism, the atom cannot go back to the ground state. Now, here is my question to Sonali or Deboprotim, who can understand, whoever can answer. Now, can you tell me what do I mean by the atom cannot go back to the ground state? What am I actually meaning? Can anybody guess and tell me? What do I mean by,
Irreversible system.
huh? Right, right, right. Sonali, can you understand? Or Pratiksha, I mean to say those whom I can see. So he has guessed it right. That means it cannot go back, that it is not a pendulum, that it will come back to the ground state. That's it. That is what I tried to make you. So here you see that if the atom is decaying from the nucleus, if it is emitting a photon, the photon has got innumerable amount of chance. It can be here, it can be here, it can be here, infinite amount of ways. But a pendulum or a ball or a classical mechanical system has not deal with infinity. So spontaneous emission is an irreversible process. I have got other slide video which I will send you, where you can see that uh, even if it is come back, even if it has got a chance to come back, it will lose its energy in the meantime, and you cannot say that where it is actually coming back. That means it is an irreversible system, which is not a classical system. And that is why you see here that classical theory, or I would say classical field theory, is something where the value of the field at any point of space can be determined by a set of equations. Now, here is a point. I am not saying about only Einstein field equation. Field equation can be Newton's gravitation law is also a field equation. Maxwell's law are also field equation. I mean, so anything that deals with field means an area where each and every point is being guided by a law of equation of motion. That is a field equation. There are many field equations, right? So here you see below on the right hand side, there are certain initial conditions, whatever be the initial conditions, and the future behavior can be guided taking into account the initial condition, because there is nothing spontaneous. It is all well guided by our classical field theory. So here is the limitation, that when Edwin Schrodinger formulated, sir, if a normal coin where both head and tail are, just a second. Both head and tail are there. One cannot tell the outcome of a toss, but still there's a classical system with a probability, not a determinant system. Absolutely, you're right. Absolutely. So here you see what is happening over here is that when Edwin Schrodinger framed this Schrodinger's law, this is more or less equals to F equals to ma, right? It is a classical system. It is a classical evolution of a quantum system. I mean to say the laws of the Schrodinger equation is classical in nature. But the problem is that Schrodinger equation, which I'm not covering in today's lecture, is that Schrodinger equation does not take into account the relativistic effects. Relativistic effect. That means what relativistic effects means, it does not take into account what is called the Einstein special theory of relativity. Now, can anyone tell me that who was the person who first framed Schrodinger's equation into relativistic effects? Any idea?
Flying Golden.
Partially right, Ikshu, but not entirely. Any guess?
Sir Dirac.
Absolutely. It was Paul Dirac who first determined the relativistic equation. That means Schrodinger's equation is now considered fully in accordance with special relativity. Now you see now why I talked at length about classical and quantum system, because what you think quantum physics is probability, no. This is the basic idea, that the predictability is being guided by a set of laws or logical rules which does not deal with infinities. Schrodinger equation was initially also framed in order to make things happen on a classical nature. It is basically the quantum wave function, as you can see on the left hand side. It carries the Planck's reduced constant h bar, followed by the x comma xt. This is a position momentum of the electron. And on the right hand side, you see the rest of the thing followed by the psi x comma t. But the thing is that it is not relativistic. So how will that relativistic effect come into place? That was done by what Issue told Klein-Gordon equation and Paul Dirac's equation. And I remember that wonderful quotation of Paul Dirac. That is called, he told that if you pluck a flower on earth, then you move the farthest star in heavens. That means each and everything in this universe is related to each other. So this is the reason that we call general theory of relativity is classical in nature, and how it differs from I would say quantum behavior of particles. Okay, everybody all in line with me? Are you not feeling bored or something? You're all good, finding it
Yes,
interesting?
sir.
Okay.
Yes, sir.
Okay, great. I'm so happy that there are a lot of women who are joining in, because last lectures when I started, there were no women or girls who are joining. And feel very happy that you should come forward, all the girls and women, make more participation, because that is how what is required. When we saw the relativistic mass equation, and when it gives infinity, why we can't use Ramanuja's infinity formula? I will talk that about later, because this would again take a lot of time, because it is off topic. So I'm so sorry for not answering this question, but I will definitely take into account into this once I complete this part. Okay, so this is a very important live lecture which you can follow in my channel. Why is classical system important? And I see most of the students not paying attention in understanding the true nature of classical physics, but constantly gives on understanding on what is called. So you can look onto that. Okay, I will come to the evolution of special relativity, which you already know that these are the papers which were shared by Albert Einstein. This is the cover. So I will just skip this part and directly come to this one. So it was initially Michelson-Morley, the ether experiment. Okay, there's another important thing which I don't know whether you know. Now, before the formation of Lorentz transformation, this French mathematician Henri Poincaré, he formed something which is called Poincaré's groups. And much earlier to Lorentz transformation, Henri Poincaré's group was actually giving the answer to Lorentz transformation. But as you know, in history, everybody doesn't get a recognition. So Poincaré's group was not considered, and it was taken up by Lorentz. So the real motivation behind formulating special relativity was the invariance of the speed of light and inconsistency with electromagnetic theory. Remember, when James Clerk Maxwell framed his electromagnetism, he also thought that there is something which is a ether. Okay, now the problem was that how could this electromagnetism can be taken into account with ether? It cannot be done. Why? Because Michelson-Morley has already proved that ether doesn't exist. I will put the collar mic. I will try to speak loud, because if I hold it for a long time, ether doesn't exist. So that is what it is called. And obviously, the experiment found no detectable. Now here we come to 1905. Let us step back to 1905 at a Swiss office at Bern, when Einstein was not known to be Einstein. And you see the wonderful quotation that he makes: that worldly cloister where I hatched my most beautiful ideas. This is amazing. I mean to say, nowadays, we say that we need a quiet place to work, we need an air con, and we need a, pen, something people would need not disturbing. You are all aware that this was the patent office where a lot of people were coming and talking, etc. And there was a lot of disturbance. And this is the table where Einstein worked, and this is the glimpse of the Swiss office. And in between this shouting and chattering, etc., he could find what is the most beautiful ideas. So what was the idea? That special relativity, which tells that the laws of physics are invariant and identical in all frames of reference, and speed of light is constant in vacuum. Now, I would like to pay an attention, take a note to all the participants who are listening to me. I'm very thankful that you're listening attentively. What I have written on the left hand side, that the laws of physics are invariant. I should not write the word identical. That is a mistake. Invariant means what? Achal, do you have any idea? What do we mean by invariant? Or Sushma or Sonali, anybody can tell, what do we mean by invariant in physics?
Unchanged.
Unchanged. Yeah. So what
Not
will
changed by
not change? Yeah. So what will not change? Any idea? What will not change? The laws of physics won't change.
with laws of nature.
Right. The laws of physics. Now, this concept actually gave rise to tensors. I will show you how. But remember this one, that the laws of physics will be unchanged. Now, here you see, this is what is called, I will give you a link where I have talked in detailed about what is called the equivalence principle. So just to tell you in very short, that if I'm sitting right now on my room and I'm sitting on my chair, so I feel a pressure of the earth right on my feet. And if the same pressure I feel when I am climbing up on an elevator, okay, so this is what I'm doing, I'm climbing up the elevator, it is also giving a thrust. And taking ideal conditions, remember these are ideal conditions, you cannot see, you cannot hear anything. So if I sit right now and I put the legs on the floor, the pressure that I feel here is the same pressure that I'm going to face if the lift is moving up and I'm standing over there. Till now, is it clear? This point, is it all clear to all of you? The equivalence principle.
Yes,
Yes.
sir.
Okay. The same happens if, God forbid, today, tomorrow, if I jump out from the fourth floor of my building, free space, right? The box is falling freely. That means the elevator's ropes are cut and the box is falling, falling, falling. Same feeling I would get when I'm falling freely from the space. Feeling, I'm talking of the feeling. You might argue with me how it is going to happen, this, that. No, these are Gedanken, a German word for thought experiment. So there are no ifs and buts, it is just if, suppose. Now this is called, what is, do you know what it is called? It is called the happiest moment of my life, which Einstein told. And that was done at sitting at that patent office at Swiss office. I have taken few lines which you can read. I don't know whether it is very visible or not. Let me magnify a little bit. You can see I have taken it from Einstein Papers, Princeton's website, and I have underlined those what are exactly written by Einstein. That the idea, you see, he writes first that electric field arises if the magnet is at rest and the circuit is moved. Now you see here, is not talking about gravity at the first go. And do you know why he is not talking about gravity? Any idea? Any idea why he's talking about Maxwell's electromagnetism? Any idea? Anybody can tell? Any wild guess? Why is talking about electric field and magnet, etc.? Why?
So it's
He
a
is talking
linear
about
theory.
relativity.
Yeah, definitely he's talking about relativity, but why is he talking about electric field and not anything frame of reference or anything else?
So because it is a non-linear theory and gravity is a, it's a linear theory and gravity is a non-linear theory.
Yes, partly, but the basic reason is that, he actually, the first thing that he tried is to unite Maxwell's electromagnetism with special relativity. That is why the first thought that came in Einstein's mind is to unite electromagnetism with his special theory of relativity. So here you see electric field arises if magnet is at rest, this. Instead, the current is in the conductor is created because the electricity is dot dot dot. Then you see the second paragraph, he tells that therefore, the existence of the electric field was a relative one depending on the state of motion of the coordinate system, and only the electric and magnetic fields combine. And lastly, he writes, this phenomena of magnetoelectric induction forced me. Read the last line. Sorry. Yeah, read the last line, last red line. This phenomena of magnetoelectric induction forced me to postulate the principle of special relativity. What was the principle of special relativity? That the laws of physics have to be same in all admissible frames of reference, which I have written here. So why I showed you the exact writing of special relativity, so that you really get an understanding. Also, you see he writes over here that in an example, you see that he writes, worth considering. Okay, let me zoom it further to you. The box, this one. Read this carefully. the gravitational field has a relative existence only in a manner similar to an electric field. And because you see this one, the italic, because for an observer in free fall from the roof of a house, there is during the fall, at least in his immediate vicinity, no gravitational field. Immediate vicinity. Now I will come to somebody who talked about topology. Who was that who was telling me what was topology? Anuj was telling me, right? Now, because topology deals with the global aspect of the surface, we don't deal with topology in gravitational field, which is very local in nature. And you see, Einstein has written, because, again read it, for an observer in free fall from the roof of a house, there is during the fall, at least in his immediate vicinity, there is no gravitational field. And now you see, right, because if there were just one single thing to fall in a gravitational field in a manner from all others, the observer could recognize from it that he is in a gravitational field and that he is falling. But if such a thing does not exist, that means he's saying that there is nothing as gravitational field, as experience has shown with high precision, then there is no objective reason for the observer to consider himself as a falling in gravitational field. This is considered to be one of the most revolutionary idea in physics till now. The Einstein's idea and the apple falling on Newton's head. Right? So he tells that considering that there is no within that local area, there is nothing called gravitational field, that person will not feel anything as gravitational field. And this actually shows our first clue that why gravity is not a force. Because if I am falling within that vicinity, there is nothing called gravity. And if you go to the Princeton papers, I will send you the link, you will see first he tried to unite it with electromagnetism, and then he went to the equivalence principle. Is it clear till now, or is it becoming too boring? You can talk to me. We are going nice and fine?
Yes, sir.
All of you?
It's fine, sir.
All of you? Okay. So here is the what I called is something, I repeat it in the same fashion. So you see this, is time dependent on gravity? Oh, in terms of general relativity, we don't have any notion called time. Time is just another coordinate. I will come to that question. Dependent in the sense I don't understand. I will let you know. Okay, so here it is, and here you see that is the same thing. I mean to say that g and g. So acceleration is equals to the gravitation. So a equals to g. That is how things become. Yeah. So that is how the g, that is a g, the gravitational acceleration is the same as a. Okay. So here I have just explained that why it is local, because remember that when we are talking about general theory of relativity, we are everything taking local in nature. Local means that particular region. So if I'm taking my mobile over here, that means if I'm taking the gravitational acceleration or anything happening to this, it is very local. So if I take only the Earth, it is again local. If I take Earth and Jupiter and Saturn, again it is local. So everything is very local in nature. Local in the sense, I mean to say, I will come to what do you mean by local. It is called manifold. I will come to that. So till now you understand that is something which is very local in nature. Okay. So here is the same thing. I'm just skipping this one. So now you see that what he says, that if you make the shine the light from an elevator, which is going in here, and the elevator is climbing up in this fashion, instead of straight, the line, the light will bend, and that actually gives an idea that why gravity is a curvature of space-time, because Newton taught us that there is a rectilinear movement of line. The light would move in a straight fashion, right? Instead of that, it is bending. So that is why we call it is the bending of the light is due to the curvature of space-time. This is just a thing which I wanted to know. I mean to say, let us not go details. There is something which is called Eotvos experiment, which is done by Roland Eotvos. He is a very famous person. The Asteroid Institute of Geophysics, a lot of things are actually made by him. Now he is the first person who actually measured this equivalence principle. You can read this. This is the single torsion balance, and it actually shows that the correlation between inertial mass and gravitational mass, The two were one and the same. So Eotvos actually made few of his students together, designed a kind of an instrument, and told that the same equivalence principle follows. And not only that, his final results, which was published in 1909, showed that there is no measurable difference between inertial and gravitational mass, very, very small, 1 part in 200 million, so we can ignore that. And it was also Albert Einstein who actually found him the best candidate for the Potsdam Institute of Geodesy. So it was Laurent Eotvos who first demonstrated through experiment that yes, gravitational mass and inertial mass, there is absolutely no difference. All okay till now? I mean to say, now we are coming to the heart of our webinar, that is the general theory of relativity, more into the real mathematics and things like that, right? Achal and others, all you're okay? Don't take me wrong,
Yes,
I'm just
sir.
random names, right? Okay.
Yes, yes. Good.
Okay, so I will just quickly tell you that why we know that during Einstein, Newton, okay, let me show you the figure, you will understand that time is different, space is different, and all the physics were taking place, like momentum, motion, torque, rotation, gravity, etc. All were taking place in this year, in this part. Now, why Einstein suddenly united all this into one area, what is called space-time continuum? What was the reason? Now, there were a lot of reasons, but to make things easy is that you read this properly, you will understand that there is a concept of simultaneity. I won't repeat that. You know, all know special relativity, how time, etc. So what it showed that two events happening simultaneously at one point in space may not be simultaneous for an observer in another frame of reference. So if there is nothing which is called, simultaneity in terms of one frame of reference and others, so there is no concept of now and then, because each frame of reference will measure it on in its own way. So if there is nothing called now and then, what is now and then? This is time. So why don't we shatter or we move away? I'm so sorry, I should say we remove the concept of time and make it something into what is called space and time in one
Sir,
single thing.
point.
What are inertial mass and gravitational mass? Orko, I would say you can go back and read a little bit, because this is not that. Again, I have to go back to, what I would say, Newtonian mechanics, and have to make you understand. Anybody can hear, can tell. So, I mean to say, inertial mass is, what I say, a measure of an object which is resisting against the acceleration. That is called inertial mass, which has got an object's resistance in order to apply, or in order to move that. That is what is called inertial mass. And gravitational mass is what you all know, right? I mean to say, that is gravitational mass, which the mass which is the g, right, by the strength of the gravitational force which is experienced by a particular body. It can be a stone, it can be everything. So that inertial mass, that it is resistance to move, and the gravitational mass, which is determined by the strength of the gravitational, I mean to say, the gravitational force, both of them are equal. So that is what is called inertial and gravitational mass. Also, what we found is that Einstein, I mean to say, Michelson-Morley experiment told that the speed of light is constant. So if speed of light is constant, if there is a relativistic simultaneity, there is nothing called now and then. Do you think there is any logic to keep time as a different coordinate? Because we are already putting special relativity's equation into Maxwell's equation of electricity and magnetism. Things were becoming too difficult. So if we remove the concept of time as a coordinate, then things become easy. So just read the red one, that the curvature, the different observers moving at different speeds will have different light cones. So your light cone, my light cone, her light cone, his light cone, all are different, right? That means it will blur. That means it is not required that the lines between that has happened, is happening, will happen, because everyone measures it at their own light cone. So this is the reason that we actually remove the concept of time, and space and time is taken into one single form, which is called space-time continuum. That means one continuous thing, which is the space-time, one lump. And that gave us actually a lot of easy things to do also. Okay, any question till now? Any question? All okay?
Sir, can you repeat the
Yes.
point of simultaneity?
Simultaneity means what? That what I am observing and what you are observing is not the same. I have a different observation, you have a different observation, different people have different observations. So if different people have got different observations, how many time coordinate will I maintain? You tell me. We have got 38 people right now listening, including me, 37. So if 37 people have 37 time coordinates and this 37 time coordinate needs to have different equations, life will become a hell. You got my point, Uttam? So that is why the concept of time was removed. So space is space, time is time taken together into one lump, which is called space time. Right? There are an absence of physical quantities. Why we in physics there is absence of quantities, heat and cold, and absence of light, absence of sound, class. Then, sir, why is not time? Why it is not in applicable in times? I don't get your question. Absence of heat is cold, absence of light is darkness. Ideally, you can come back to me once I complete. I cannot understand. I mean, it's heat and cold, what it has to deal with time. Anyway, so the Maxwell's equation were actually a set of 20 equations. Just to give you a little bit of knowledge, that this was the person Oliver Heaviside who first reduced all those 20 equations to these 4 equations which we read in our book. Right, so this is the contribution of Oliver Heaviside. So you can go to my this video. It's a very interesting video made long back, which is talks about the Maxwell's equations, a brief history. Okay, so just to summarize for the how much, yeah, almost, yeah, what we have learned till now, the general relativity is more of a geometry. The bending of light shows that there is a space-time curvature, and in order to make the laws of invariant nature invariant, Maxwell's equations are put in order with special relativity. Now here comes what I was asking to Achal and Sushma and Sonali, that why do we measure the curvature and how do we measure so that the curvature keeps the laws of nature invariant. Now we are coming to the real part of the general theory of relativity. So I will just have a water and then we can go into the real part. You are all enjoying. I mean to say, you are very silent, so I really cannot understand. Are you getting things good?
Yes.
Yes, sir.
Okay.
Yes, sir.
Okay. Maybe you are all listening very attentively. That is why. Okay. So from flat space-time, we move to curved space-time. So here is again a quick review of what we call is the principle of postulate. That is, the laws of physics would be the same, and equivalence principle, we have already looked into it. Okay, now you should pay a little bit of attention. Here comes a little bit of mathematics, not very difficult. So you see here, if I take a flat space-time and if I try to measure a vector, which is the A vector, if I put it in a curved space-time, you see the vector remains the same. But what changes are what? The components of the vector. So ax becomes a longer a prime x and ay becomes a little bit longer a prime y. So the objective of designing general relativity is that from a flat space-time, we have seen that why it is a curved space-time. You don't have any doubt, right? But when we are moving from flat to curve, remember that vector cannot change. If the vector changes, then we have a problem, isn't it? So here you see again, I have rotated the vector. The left hand side is the original and the right hand side is the rotated. You see a prime x is bigger, a prime y is shorter. Are you getting my point? What I'm trying to tell? A change of coordinate, you can understand, but the vector should be the same, isn't it? All of you there with me? Yeah.
Yes,
Yes,
sir.
sir.
Yes, sir. The four
Okay.
components change, the vectors are remain same.
Absolutely, absolutely. Now here you see what I have told, that in flat space-time in Newtonian physics, vectors are good enough to do the job. But in a curved space-time, we cannot do this. So what is the now you see this is this one. That is what I was saying. What is the surface on which this geometry takes place? That is a curve. Now I will tell you a little bit that this is actually I won't do because it is already almost 9 o'clock. I have to cover up other topics. But remember one thing, all my dear students, shall I call students, seniors or juniors, whatever. Remember this thing very
Yes.
closely. Remember this thing very closely. Please do not jump into the mathematics of general theory of relativity without understanding non-Euclidean geometry. I repeat it with firm assertiveness and with due responsibility that it is all about geometry. And remember, Einstein, I have skipped that part, otherwise, it will go to 12 o'clock at night. In another YouTube shorts, I have shown that it was Marcel Grossman who taught Albert Einstein differential geometry. You know the reason, because Einstein, if you read this book, I will put the name, it is called Subtle is the Lord. I repeat it, Subtle is the Lord by Abraham Pace. Pais, Abraham Pace. Here, Einstein was crying. He was shouting that, "Oh God, Marcel Grossman, save me, save me." Because he was unable to do anything related to tensors because he did not know anything about differential geometry. Marcel Grossman was far more intelligent than Albert Einstein, and he told that, "Hey, come on, I will teach you differential geometry." And that is why the problem with Einstein was not with the physics, the problem was with the mathematics. And that mathematics, the Ricci tensor, the Ricci curvature, all these are parts of differential geometry. But he never knew about that. He was not aware about that. Marcel Grossman was a master of differential geometry, and he actually taught that. And then, with the help of Marcel Grossman, there's a wait. I will just give you this link. If you can, please go ahead and watch this later. Not now. Is a I mean to say, I made this. It's a YouTube Shorts, but I mean to say it is a very good short. I mean to say, I liked it, so you can just go ahead and watch it. I'm sending this link on the chat box right now, and you can just watch it. It is called Albert Einstein's Math Tutor. Okay, I'm just sending this to you. You watch it later. You can copy and paste it. Where is the chat box? Yeah. So, and he has given evidence showing that how they, in 1913, how they developed this tensor equations with Marcel Grossman. And then Grossman died much earlier. He died at 64 years, I think. So there is the link which you can later watch it. So what is that geometry? What is the surface called? It is called manifold. Manifold means manifold, which has got manifold. And who actually coined this term? You see, this is the thing. So any surface, but any surface cannot be called manifold. I'm just giving you an example. So maybe this one can be called as a manifold. So it has got many curvatures, right? Like this. It can be called as a manifold, yes. But all surfaces cannot be called a manifold. So someone was telling, who was that? Anuj. You see, here we come to topology. Manifold is a topological space that locally resembles Euclidean. Okay, what do I mean by locally? So if I take this surface, now pay attention over here. If I take this surface over here, okay, this is a crumped up surface. Now if I zoom it further, finally it comes like a flat surface like this. Locally Euclidean means I can use differential geometry, calculus, mathematics, whatever. It should be locally Euclidean. But if you zoom out, again it will become a manifold. So that is the definition of a manifold. All surfaces are not manifold. There's a criteria. I'm not going into all those mathematical details. Here you see. So this is the man who is walking on a sphere. All of you can see. Now if I zoom it further, it will become flat. Something like this. Here you see. The lines are meeting, it is a positive curvature. The lines are straight, it is zero curvature. The lines are diverging, it is called a negative curvature. Now here you see what happens if I zoom it. Now I will try to zoom this. So can you see these boxes? So don't you see these are the boxes where I can use differential equation, integral equation, everything related to calculus. Are you getting my point, all of you? You got my point, what I'm trying to
Yes,
tell?
sir. Absolutely.
Yeah, so this is why it is called locally Euclidean. Now again, if I zoom out, you see this will be a kind of a surface, just a surface, a sphere, a cylinder, a parallelepiped, whatever. So if I differentiate the surface further, I can apply the rules of calculus. So that is why we call differential geometry. I'm using the rules of calculus and differentiation in geometry. So that is why it is called a surface. So you see here is a curvature. Now I zoom it and zoom it and zoom it further, it will become a straight line. Ultimately, it will become a straight line. I mean to say a Euclidean surface. And in Euclidean surface, we can use a lot of geometry and life becomes easy. So this is called manifold. And here is one video, I will send you the link, that why differential geometry is shaped up general relativity. You can later look into it. Now, who coined the term manifold? I called him the grandfather of mathematics. The granddaddy of mathematics is called Bernhard Riemann. He was a very poor person, and his father actually went bankrupt to send him to Göttingen University to study under whom? Can you recognize who this other person is? Anybody?
Gauss.
Euler.
Yes,
God.
Carl Friedrich Gauss. Right, absolutely.
Gauss.
Right, absolutely. So there he was given a kind of a dissertation, and this was the paper in which he first coined the term manifold on the hypothesis which lie at the basis of geometry. And when it was done, 1854. And when did Einstein coin special general relativity? 1915. How many years? So that means the foundation of geometry or the foundation of differential geometry was made much earlier to Einstein. So don't have that notion that it was Einstein who coined the term tensor or non-Euclidean geometry. It was done even much earlier to that, right? So we come now to what are tensors. Now this is important because we are coming to the last phase of our webinar. And this is basically, it comes from the Latin word tender, which means stretch, something which is stretching. Now, can you now get an idea why we are approaching tensors? Can you guess what I am going to tell you now? Anybody? Vishwaranjan, Shankashubro, Sonali, Saubhagya, can you understand why I am talking of stretching of tensors? Any idea? Any clue?
Because of gravity.
No, absolutely not. Anything else?
Geometry of space-time.
It's because we are straining space-time, and because strain is a tensor quantity, that's why we are now talking about tensors.
Right. Because we are going, most importantly, from a flat system to a curved system, from a coordinate to a different coordinate system, right? So here you see that if I got a data, any kind of a data in the sphere, and if I stretch that sphere, it can stretch, whatever be the reason. It can be due to whatever, but it becomes an oblate spheroid. And how will I know the stretching for? Because it has been stretched. So that means what I was telling at the beginning of today's webinar, that we need to have invariant laws of physics. That means the laws of physics cannot change. Stretching, bending, whatever happens, that means I now need to design a mathematical tool which will help us to determine the law of physics in spite of stretching, turning, bending, rotation, whatever. And that is what the tensors does. Actually, tensors were invented, you can look into my other videos, to study the structure of crystals, because crystals have many different shapes, as you can see. So these were actually being invented. So now you see, this is a very interesting diagram. A person is throwing a ball, I rotate the axis. The person is throwing a ball, I extend the axis. So I am doing stretching, bending, whatever. But remember that throwing of the ball measurement should be the same. So that is why you see Einstein wrote that the general laws of nature must be expressed by identical equations relative to all other systems, whichever way they are moving. So in special relativity, we got inertial frame of reference, where the laws of physics, especially electromagnetism, were tied with special relativity. Now we are taking gravity, which is non-linear in nature and which has got non-inertial frame of reference. There also, the laws of physics have to be the same. So here is a video which you can look at, a beginner's guide on tensors to understand general relativity. So now we come to the very central part, which is called Einstein field equations. So the left hand side of the equation measures the curvature of space-time, and the right hand side of the equation talks about the matter energy content. That means if I get something like this, I cannot show you with my one hand, sorry. And if I put a heavy ball around here, sorry, so it causes a dent, right? So the left hand side actually measures how much the dent is, and the right hand side says that how much the matter, or this is just a mobile phone, if I put a heavy lead or something, how much the matter of this mobile is, which will cause a curvature of the space time, how much it will bend, right? All okay till now? All okay? So
Got it, sir. Got it.
Yes,
yeah,
sir.
okay. So here you see, when we are decoding and trying to understand Einstein field equation, some terms you already know. What do you know? You know what is a cosmological constant. You know what is 8 pi, which you know gravitational constant of Newton. You know what is c4, that is the speed of light taken into 4 dimensions. From 3 we are moving to 4 because length, breadth, height and time. So taken all together, 4-dimensional space. Achal was telling that we cannot, visualize that. Okay. Now, I see, to be very honest with you, each of these components will require at least 1 hour time to explain mathematically or intuitively, as you understand. So I will just give you a very overall idea. There are videos which I will send, you can later watch. Each one of them will take a long time to watch. As in GR we study local region, then why do we need tensor? We need tensor because the tensors are basically dealing with the change of coordinates, because tensors deal with coordinate changes, because tensor are components where in spite of coordinate changes it won't change. I think, Shubhra, you are getting confused with the global part. Don't think anything is global. We are not dealing with topology. It is a different branch of science. I've got videos, we can take a webinar separately on topology. Local means to that region, to that space where the gravity is taking place. That's it. So you can see the R talks about what is called the Ricci curvature tensor. That means how a volume of matter changes when it moves through flat space-time to curved space-time. Let me answer. So you said that gravity is due to curvature, yes, but the example you showed, the mobile pulled by Earth gravity, for celestial bodies, what is pulling them to cause the deformation? No, no, no. Celestial bodies, what is pulling them to cause the deformation? Nothing is pulling. That is the concept. Nothing is pulling to cause the deformation. All the celestial bodies are in the fabric of space-time. If they are very heavy, then it will cause a more curvature. If it is less heavy, it will cause a less curvature. As simple as that. I hope I can clear you. So mobile is less heavy, so it will cause less curvature. Jupiter is very heavy, so it will cause a better curvature. Black hole is so heavy that it will tear the fabric of space-time, and the curvature will come to infinity. I mean, it's a non-determinable. Got my point? Okay. Ricci scalar keeps track. Okay, you read this 1, 2, 3, 4, 5, 6. Let me explain you quickly what these are. Okay. This is something very interesting. There are 16 partial nonlinear differential equations involved in this single equation. It is not one equation, mind it. So mu nu 4 plus 4 plus 4 plus 4. And what is mu nu? This is called the indices of space-time. So mu nu is basically talking of x, y, z and time. So it is actually 16 equations which is framed into one single equation. So you understand how complex and difficult it is. Okay, I will leave this part right now. Here you see what you are asking. Now you see the gravitational acceleration, the g, is highest for Jupiter, is less for Earth, is less for Mercury. Why? Because of the mass density. Yes, Asif, tell me. You have a question? Okay, is due to this mass density, and that which is now called gravity, or the gravitational acceleration, small g, is basically due to the mass density of that planet, which is causing the curvature. Are you clear? I mean to say, I know this is a little bit confusing, but overall, can you get my idea?
Yes, sir.
So locally all regions are flat in GR. Yes. Flat in GR, we are dealing with only local region, then why should we care about curvature? No, 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 no. Subra, I think you're getting confused. Locally, the regions are flat. Locally, in the sense in what? Locally, the regions are definitely flat. But when we are talking of curvature, we are zooming it so much so that we can use the rule of calculus on that surface or other Euclidean, non-Euclidean or mathematical tools. We should care about curvature, then how will we know that how much curved the surface is? Are you getting my point? Locally, the things are not flat. Locally, when you zoom it, you can use calculus to calculate that curvature. It is an approximation. But definitely there are curvatures. Then why will we start study general relativity? I know this part is a little bit, but just bear with me. You will be able to understand. Okay. So first is the metric tensor. Pay attention. These are the components. Okay, there is a huge. I have got a full 1 hour 20 minutes video on derivation of metric tensor, which I will, if you want, I can send it to you. Okay, imagine this to be a space-time ruler. That means there is a blanket. Just try to imagine. Again, it is abstractness. There's a blanket, and the metric tensor g nu is like measurement on this blanket. That means how much stretched it is. If there's a blanket, you stretch it, how much squashed it is, and what is those things which are moving around those blanket. That means it is called a space-time ruler. It is measuring the amount of stretching or squishing or whatever is happening. That is metric tensor. I know that this is not very clear, but I will send you a very detailed video on that. Okay, this is metric tensor. Metric tensor has got a lot of things which I cannot actually explain in such a short time. Okay, Ricci curvature tensor is something which is easily explainable, which is done by this person, Gregorio Ricci Curbastro, who was a student of Tullio Levi-Civita. And this book that you see is actually where he coined this, used this Ricci curvature tensor. Okay, what is Ricci curvature tensor? Let me explain you a little bit intuitively. Suppose two lines from here, they are starting to move, and due to the curvature of space time, they are diverging or they are converging or they are moving in this way. Do you agree to me? It can happen. That is why when we start, when we tell that on a globe, when we start walking, we meet at the poles. You remember in our school days when we learned geography that we meet at the poles. So Ricci curvature tensor actually describes how much space-time. Now this is volume, not the person. The volume will change. I will show you the diagram now. See this. So if I take a ball, because the geodesics, I mean to say the lines are converging, so it will shrink, 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 shrink. Can you see this picture? Are you getting my point, all of you? This is very
Yes,
crucial,
sir.
right? So the first R, don't ask me that why, when, what is the derivation, it will take 1 hour. But just the first R is telling that how the volume, and this volume is the differential volume, not the ordinary volume. It is called the differential volume. It's from the first fundamental form of differential geometry. So how the volume will change. This is overall, understand, Ricci curvature tensor measures that. You see here, straight line 0, converging greater than 0, diverging less than 0. Very simple. All of you can understand? Clear?
Yes, sir.
Okay.
Clear,
Now
sir.
you see the Riemann curvature tensor. This is actually done by Bernhard Riemann. Now, what it shows, I will tell you. Now, here is a simple concept. Now, imagine it in this way, that if there is a triangle over here on this wall, and imagine that I am walking with a spear in my hand, this red one, the black one with the red dot. So if I start walking here, 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 and I go, and I'm trying to keep it straight, and if I come back, you will see those yellow lines or the vectors will come and meet on the black one. Yes, definitely you can go with Leonard Susskind's theoretical minimum, definitely. So it will come and meet at one point, right? If I try to state, is it clear till now? That if I try to walk straight, when I come back in a flat surface, where I started and where I end, it will be the same. You all agree to that, right? Okay. Now you see what happens over here. Can you see this diagram properly? Yes or no?
Yes, sir.
Yes, sir.
Okay, now
Yes, sir.
imagine this yellow vector you can see, Taran and Milton, you can see. Now imagine I am walking with this yellow vector round and round and round. I'm trying to keeping it straight, but you see it is bending, it is bending, it is bending. And this one, the purple one, let me zoom the slide, you will see this purple one. Can you see the purple one? This purple one is different from the original V. You got my point? This curvature, this one, I'm going back, and when I'm coming, this V and V prime is different. Are you getting my point?
Yes, sir.
So, but what did I tell you at the beginning? I told you that the vector should be the same, whatever the way things move. Now, Riemann curvature tensor, what it does is that it actually measures the deflection. That means how much the original vector started and how much difference is between the when I come back to this. Again, I repeating it. When I started, what was the vector position? And when I come back, what was the vector position? That difference is what the Riemann curvature tensor measures. You got my point? So if I can use
Yes,
a
sir.
correction symbol, which I have not used here, otherwise it will become too complex. It is called Christoffel symbols. These Christoffel symbols are a kind of a correction that if I say, okay, I started at 2, but when I came back at 2, there's a deflection of 0.2 degrees. Then I can use that correction term and use that 0.2 degrees and I can do the mathematical calculation. If it is zero point 0.5, it is 1, it is 10 degrees, I can really know how much is the deflection in terms of the original and the coming back after the rotation. And most importantly, you know, these are symmetric tensors. So if you move in clockwise or anti-clockwise, the measurement will be accurate. Okay, so this is the work of Riemann curvature tensor. What the stress energy momentum tensor does? So all the energy related thing of a matter. So here is a mobile. So it has got an energy density, it has got an energy flux, it has got a pressure, it has got a shear, it has got a momentum density, everything taken together. I'm so sorry. When it forms a tensor, when it forms a kind of a tensorial form, all the tensor components are the stress part is now put in this part. So now it is clear. So the curvature, whatever is the stretching, the bending, the Riemann curvature, the volume, etc., all of this I have got on the left hand side, the Ricci, the Riemann, etc. So the curvature is being measured by the left hand side of the Einstein field equation. And the right hand side of the Einstein field equation, what it does? It measures the matter content. That means how much matter, how much energy, how much density, how much energy, how much shear actually is present in this matter, which is responsible for the curvature. Is it clear, all of you? All of you clear?
It's clear, sir.
Okay. So
Yes, sir.
you
It's
see,
getting to.
okay, so now you see here that gravity is due to this curvature, and this is called a geodesic. I will come quickly to complete geodesic. So this effect is, we call it as gravity. That means the bending, it is a manifestation of the body which is present, and that body's stress, shear, pressure, etc. are measure. Now you might ask me, why, sir, we are measuring all those things in a tensor? Because everything has changed. The coordinates have changed. So how will we get that if everything is changing, then the vector should be invariant? And Einstein has told us that whatever happens, my boss, my dear boys and girls, the measurement cannot change. So that is why it is called, we are using tensors. And this is why it is, now you see, this is This was another YouTube shorts you will see in my channel. It is called 29th May 1919, when Arthur Eddington first proved that when sun and earth are coming, I mean to say there is a solar eclipse, when things are coming in line. So obviously sun is what, much heavier than earth, so it will cause a much more dent. So the star over there, the light should be coming straight. Instead of that, due to that heavy fat sun, it has caused a dent, and that is why the light has traveled a little bit on that way. And when we observed that in South Africa, that island of Principe, we saw that, oh my goodness, the light should come from here, but has the star moved? No, the star has not moved. The star is emitting light in the straight line, but because of the solar eclipse, the sun is present, and sun is so huge that the space time has bent, and the light has to take a traveling that way. Okay, so we come to the cosmology, which is the last part of our video. Everything okay? Are we all there? We can continue with this, right?
Yes, sir.
How do we visualize space-time curvature in 3 dimensions? I will come to that later. I will take up questions. Now, here is the last part. I don't know if you are aware about this great mathematician from India, Calcutta, Amalkumarraychaudhuri. This is just given an idea. Now, why I'm talking about Raychaudhuri equation is that general theory of relativity definitely deals with black holes and a lot of space-time curvature, etc. Now, the idea behind Amalkumarraychaudhuri's equation is that Raychaudhuri told that you cannot escape what is called a gravitational singularity. Now, I hope you all know what is singularity. Can anybody tell me what is a singularity? What do we mean by gravitational singularity?
It is a infinitely dense point.
Sir, it curves space-time so much that it collapses into itself.
Yeah, in some way, in mathematically, we call singularity something where the answer is undefinable. Infinity is something else. We can define infinity, but it is undefined. Let me show you. This is a very unique thing. Have you heard about AKR, Amal Kumar Raychaudhuri and Raychaudhuri equation? Anybody
Yes,
knows
Yes,
we
sir.
about?
did a podcast with him.
Yes, sir.
Yes, sir.
Okay. So this is the Raychaudhuri equation, right? All are the same. But what it tells you, see, that it talks of a term which is the sigma term, which is called the shear. You know what is shear? I mean to say, I don't have to explain, right? So unlike what the universe, it refers to the shear, that it will be something like this. I have got a very long video of 57 minutes on Raychaudhuri equation explaining a lot. But here just understand there is a shear element, and there is a rotation element also, because the universe is rotating also, and the omega term actually talks about the rotation. So rotation definitely takes a very important role, right? And there is something which is called a expansion scalar. I will come to that part. Scalar expansion of the universe. Now you see there is an important term which is called homogeneity and isotropy. Homogeneity means that the universe looks same at every point of time. You see here, there, more or less, the universe looks the same, right? There are no special or preferred locations. But there's something called isotropy. So isotropy means the universe looks the same in all directions on an average. There are no privileged locations. That means homogeneity tells that energy, density, pressure, and temperature are constant, and isotropy, they're constant but in every direction, do not depend upon the direction. So you see the balloons, the lines, the red dots, imagine them to be the planets or the galaxies. So the universe is expanding, more or less it is isotropic, so the distance between them, etc., the same, and it is homogeneous. Now, this is what is called the Friedman-Lemar model of cosmology, where we take for calculation, for like just like we call it as a Schwarzschild metric, etc. So for the idea of what I would say easy calculation, we say then let us assume that it is homogeneous and isotropic. Now, AKR, Professor Raychaudhuri told no. He told no, that homogeneous or isotropic universe cannot be an ideal universe. So here you see I've just taken this pizza example. Evenly distribution of pepperoni or olives, etc. This represents homogeneity. That means wherever way you rotate, you will get the same pepperoni or same olive, etc. Right? So does the distribution of toppings change? No, because it is isotropic. There are no preferred direction of the toppings. Okay. Now you see what that how AKR arrived at this equation when Einstein's field equation. So Edwin Hubble and Milton L. Humason actually, when they observed, they found that the universe is expanding. And here you see that Alexander Friedman, the Friedman-Lemar model, they assume that one, homogeneous, second, it is isotropic, and third, it is static. But we will consider homogeneity and isotropy for the time being. So the Friedman-Lemar model, which is this one, actually tells that it is a exact solution. So there is a homogeneity, there is an isotropy, and there is an expanding universe. But there is a problem. There's a big problem. The problem was that if the universe is expanding right now, then at some point of time it should be less, and it should be very small. What Taran was telling, that it was infinitely small and infinitely dense if the universe is contract at some point of time, if we go and trace back the time to Big Bang. Are you clear till now? I'm trying to tell you why we know that the dark energy is increasing with expansion of the universe. So, no, it is not violating. I will tell you why. Now you see how AKR arrived at the equation. He thought that the universe at a finite time was reduced to a point where the matter content of the universe was finite, and other conditions like temperature, etc., would become also infinite. So remember, AKR's model or the equation did not comprise of homogeneity or isotropy, right? Including rotation. So what he did is this one. So he thought that is the cosmological singularity generic? Is there any non-singular solution? That means, is there any way in which we can escape singularity? And the answer that he found is no. We cannot escape singularity. And this is what it shows. Assuming that there is a zero volume is reached at infinite past, there was a minimal volume. Our theoretical module obviously shows that we had a finite past. Giving up homogeneity, I am highlighting this part again, this one, which I am highlighting right now. Giving up homogeneity and isotropy would not help. Only if we include rotation, which is the omega terms, possibly we could escape the Big Bang, but which is not possible. So this minus term and this minus term actually shows that if we get back to time, there is no escape of singularity, we are getting negative. But here you see, I have shown there is a positive term, this one, this positive one. This positive one, why? Because it shows that there is a rotation. So AKR tried to include the rotation as 2 omega square. Possibly if we could include rotation, then we could escape a singularity, but it is not. Or maybe quantum gravity could give us a solution. So that is what AKR's equation is, that it is so very important. And I will tell you, if you go to my other video on AKR, I will also making another video talking to Professor Shayon Kaur of IIT Kharagpur, and he is a master of amalkumarraychaudhuri's equation. Remember that AKR's equation is so important that it goes beyond general relativity. It can be applied in fluid mechanics and many other areas. So it is called congruence of time like geodesics. I'm not confusing. I won't tell you like that. What is that? So what it showed is that there is no escape from singularity until and unless we include the rotation part. And here you see, I have told, this is a little bit one. This is the acceleration. So the second derivative of, the second derivative with respect, if you go back negative, the whole universe is going to contract. The shear is also negative, so it would hasten the gravitational collapse. That means the star or the universe is moving towards collapse, and only omega plus would give us an escape from singularity. So what happened to the universe or a region to the universe, if we include the conditions, there can be peculiarity of motion associated with shear. So this double dot also shows that by tracing back in time, we cannot escape singularity. The shear also tells that there will be more singularity, only and only including positive omega square, we can escape singularity. This was what is called the Raychaudhuri equation. Why it is important, you will be surprised to see that at singularity, all physical laws break down. From a geometric point of view, can be defined in terms of geodesic incompleteness. I'm not going into these details. Now, Professor Parthosarathi Majumdar from ICS told actually that Einstein's theory was a fundamental limitation, and during that old days when AKR formed that, it was challenged to Einstein's general relativity, and Raychaudhuri equation establishes a kind of a limitation, telling us that a typical space-time singularity cannot. And you know who used this equation? It was Stephen Hawking for the use in this book, The Large Scale Structure of Space-Time. You see, I have taken lines, I have quoted, I have taken screenshots. Equation 4.3.5 is the analog of Raychaudhuri equation. Again, he uses this time. Numerous occasion, Stephen Hawking and Roger Penrose, in their book and in their equations, numerous times have used what is called AKR or the Amalkumarraychaudhuri equation, because they are also targeting that the singularity is inevitable, is inescapable. Now, Roger Penrose got the Nobel Prize, Stephen Hawking did not, but this was the work of Amalkumarraychaudhuri, and it actually has been used many times by Roger Penrose and Stephen Hawking. So that's it for today's webinar, and I would like to immensely thank you immensely for watching. Now you tell me, how did you like and what is your opinion about it?
Sir, I found the session very intriguing.
Okay. Okay, anybody else? Anything?
Sir, the session was really helpful, and the physical explanation of the things was really helpful.
You learned something new, right? All of you,
Yes,
Ikshu
sir.
and others?
Yes, sir.
Okay, great. Okay, so what we do is that let me first put a pause to the recording part. Okay, let it be. Yeah, I'll just put a stop.